Today, humans are having a vast impact on our planet. Whether it's extracting natural resources, providing energy, gathering food, or just going about our daily routines, we're having a huge impact on our planet. We are literally changing our Earth. As with change comes consequences. There's an increase in the frequency and intensity of storms, fires, earthquakes, tornadoes, and other natural disasters, and the associated devastation. As population continues to grow, we're putting more stress on our natural resources. We're finding new ways to stack people on top of each other. Areas already troubled with excessive population growth are expanding upwards and outwards into areas that are already problematic. We're to the point where every time it rains, the health of our oceans are being significantly impacted. And I'm not just talking about rain on the coastal plain. These problems occur all over the world and run off into inland rivers, making a long journey to the ocean, rapidly creating negative, long-lasting impacts. Our ocean's health is essential for the stability of our life and for our planet. So there is a problem, but there's hope. We're all contributing to this problem in some way, whether it's us driving our vehicles or buying produce or heating and cooling our homes. I'm not saying that these activities are wrong and I'm not a part of the problem. But why are we here? We're here because we know there is a problem and we want to help find solutions. The good news is that there is a reason for hope. We're at a very new and exciting time in technology where we can process large volumes of data quickly and share algorithms that help to turn data into valuable information. Never before have we had access to so much data and analytical capabilities to help us understand and mitigate these problems. The Internet of Things promises new capabilities to integrate, connect, share, and scale up our analyses. Machine learning is being applied to help solve more problems. We're getting data in near real time, and as a result, we want to be able to provide answers in near real time. Our planet is complex and constantly changing. We use satellites to help us monitor our planet at regular intervals. Some of these satellites are equipped with sensors that can help detect phenomena such as fires, moisture, vegetation, and temperature. Some of these systems have been collecting information for over 4 decades. This information is collected and stored in scientific formats and made available through data centers, the very data centers that several of you in this room manage and support. Some of these foundational layers can also be found in Esri's Living Atlas of the World, ready for you to help to use and increase the value of your work. In addition to the vast array of land sensors, there are also sensors that help detect phenomena in the ocean, such as chlorophyll concentration. Chlorophyll is observed through small microscopic organisms called phytoplankton that feed on nutrients in the water. Chlorophyll is present in their exoskeleton. Although the sensor is not directly mapping the nutrient concentrations, the association between the phytoplankton and nutrients they feed on serves as a proxy to detect nutrient concentrations at or near the ocean surface. This gives us the ability to map, analyze, quantify, and be able to detect changes and trends in chlorophyll levels. This is a fundamental aspect of understanding our planet. This data can be used to better understand and quantify temporal trends in chlorophyll concentrations, and we have observed these values changing over time. Chlorophyll trends are used to help understand primary productivity, which can be linked to the success or failures of regional fishing efforts. Esri, along with a set of core science community partners, is working towards developing indicators that help monitor chlorophyll levels across time. We are all working towards addressing Sustainable Development Goal 14, life below water. For this project, our partners are the United Nations, the Group on Earth Observations, and the National Ocean and Atmospheric Administration. The 2030 United Nations Agenda for Sustainable Development provides a shared blueprint for peace and prosperity for people and the planet now and into the future. At its heart are the 17 Sustainable Development Goals, which are an urgent call for action by all countries, developed and developing, in a global partnership. They recognize that ending poverty and other deprivations must go hand in hand with strategies that improve health and education, reduce inequality, and spur economic growth, all while tackling climate change and working to preserve our oceans and forests. This agenda is a plan of action for people, planet, and prosperity. Esri is helping by executing methodologies that have been proposed by the team, conducting global analysis on large volumes of chlorophyll data, and helping to design and implement information products, reports, and dashboards. We've been working with the team for just over 5 months, and today I'd like to share some of the workflows we've implemented and the progress that we have made. To date, we have been able to gather the monthly chlorophyll data and the associated data centers and compile it into a file geodatabase. Then we created a mosaic and added the rasters to a mosaic. Once the images were loaded, we were able to apply raster functions to visualize the layers and commonly accepted symbologies that are easy to understand by the scientific community. Here is one symbology commonly used by the NASA community, and here is another commonly used by the NOAA community. These raster functions are managed in the mosaic and apply 2 simple functions to generate different renderings. This is achieved by applying a remap, which bins the pixel values into numeric groups, and then by applying an attribute table function that allows you to assign colors and names to each one of those bins. Pretty simple. By dynamically applying these function templates, I can see different visualizations without creating redundant data. These processing templates help visualize the different phenomena and have useful color breaks associated with thresholds in the data that can help distinguish higher and lower concentration values. Now that we have the data loaded and we have it symbolized in familiar ways, we can start conducting a spatial analysis. This is where some of the new multidimensional analytical tools can really help us unlock and visualize trends and patterns in data that would be otherwise unseen. The following 5 multidimensional analytical tools were used to help better understand chlorophyll in our oceans. Generate multidimensional anomaly, aggregate multidimensional raster, generate trend raster, create space-time cube, and emerging hotspot analysis. Pro 2.5 will be an impressive release. We will have exciting new tools that I have been able to use for this collaborative project. Coming in Pro 2.5 is a updated set of multidimensional analysis tools. These tools allow you to perform analysis on scientific data across multiple variables and dimensions. These tools are aware of the dimensionality of the data. Multidimensional data represents data captured at multiple times and depths or heights. This type of data is commonly used in atmospheric, oceanographic, and earth sciences. In ArcGIS Pro, you can manage, visualize, and analyze multidimensional raster data in multiple formats, including NetCDF, HDF, GRIB, a multidimensional mosaic data set in Esri's cloud raster format. In addition to the geoprocessing toolbox you're probably familiar with, the multidimensional tools are also available through a new multidimensional ribbon. When a multidimensional layer is selected, this ribbon appears and gives you access to a subset of multidimensional tools. The first tool that we're going to utilize is Generate Multidimensional Anomaly. This tool computes the anomaly value for each slice in a multidimensional data set. It takes into consideration the entire span of data and computes a normal value. Then it compares each slice to the normal and calculates the difference from the normal value for each pixel. In the case of chlorophyll, these anomalies can be associated with red tides, harmful algal blooms, and eutrophication. The output of this tool is a CRF that contains a slice for each month, 228 months total. We can verify this by looking at the properties of the CRF and inspecting the source info. Each pixel's values represent the distance from the mean, the value above or below the considered normal. Changing the symbology helps emphasize some of the more problematic areas. Using the time slider, we can display a temporal animation. This is very helpful for visualizing the changes over time. Visual inspection can be quite tricky and deceiving. The temporal profile tool helps us quickly visualize change over time in a chart. This tool really helped me explore chlorophyll over time for a certain location or area. I can even create custom areas on the map and start to compare them. Using the temporal profile tool, I start to get a handle on how chlorophyll values are changing. This is a great tool for dynamically exploring the different regions. Next, I was interested in looking at longer-term trends. The Generate Multidimensional Anomaly tool provides a good idea of how values are changing month to month, but the natural seasonality in the data may obscure some important patterns. A more objective question is what is the trend from year to year? To help answer this question, I used another multidimensional analysis tool, Aggregate Multidimensional Raster. This tool generates a multidimensional CRF by aggregating existing multidimensional dataset variables along a specified dimension. This tool was used to take the 228 time slices and create a single slice representing the average chlorophyll values per pixel for each year, creating 19 slices for a total of 19 years. This process is looking at each individual location over time independently and unaffected by neighboring pixel values. Now that we have aggregated our monthly data into years, we are ready to estimate the yearly trend using the Generate Trend Raster tool. This geoprocessing tool estimates the trend for each pixel along a dimension for one or more variables in a multidimensional raster. For our output, since we selected linear trend, each pixel value represents the slope of the trend line. Positive values indicate an upward trend, and negative values indicate a downward trend. Let's look at the results by exploring a few places around the world. Remember, the deeper the purple, the more upward the trend, and the deeper the green, the more downward the trend. The white areas represent areas where no significant trend is occurring. Now that we've conducted our multidimensional analysis using this, we're going to use a space-time pattern mining tools to see if they can help us uncover some of the patterns in our data. This tool we're going to use a create space-time cube from multidimensional raster layer. This tool takes a multidimensional raster layer and compiles it into a space-time cube. The output is a netcdf file that can be used with the tools in the space-time pattern mining toolbox. We heard about the emerging hotspot analysis tool just a moment ago from Lynn. This tool performs spatial analysis, looking for areas that have significantly higher and lower trends. Higher or lower levels of chlorophyll when compared to the overall global level of chlorophyll. It then looks at those hot or cold spots across time to see if there are temporal patterns such as location always being a hot spot or always being a cold spot. The dark red we see areas we see close to shore indicates these areas have been a persistent hot spot over space and time. A persistent hot spot is a location that has been statistically significant hot spot for 90% of the time step interval with no discernible trend indicating an increase or decrease in the intensity of clustering over time. So after I had a chance to review the results, I decided to see if there was any supporting articles or similar that could help me build confidence in these results. I've embedded some of that information here into this story map. Here we can look at the information up in the Puget Sound, and we can verify that there is a decline in the ocean health in that area. So this helps me validate the information of the results that we're seeing. So you've seen that there's great value in sharing the chlorophyll layer and being able to access pixel-level details for the entire archive of the data volume. You can conduct some impressive analysis, but when it comes down to it, we need to consider sharing an information product rather than sharing just data. We've analyzed the data that was archived at a data center, but we're still talking about pixel values. We need to be thinking about how we can summarize the data down to a level where it makes sense and it can be easily shared and can inform decision making. So while eutrophication is a global problem, the impacts and mitigation activities take place at the local level. Next, I'll summarize our analytical results within EEZs. These are the areas which countries have control and represent the area which an individual country is most interested in. We'll summarize chlorophyll concentrations over a 19-year time span within EEZs. Using the zonal statistics as table tool, we can summarize a deep and vast archive of quickly data into a simple table. Once we have the table, we can easily associate the table with the EEZs by using a join. From here, we can publish the layer to ArcGIS Online. At this point, the data is ready to be plugged into any number of ArcGIS Online configurable apps. Since we're talking about monitoring the overall status of an SDG goal, a dashboard is a great option. I was able to assemble this quick dashboard in less than an hour. Since we have control of the data and how it's formatted and understand how a feature service can power an application like a dashboard, plugging these attributes into gauges was easy. As a part of the overall SDG initiative, we will make this ArcGIS Pro package available with detailed results per country. The concept here is for others to pick up where we left off. This is a new pattern that is emerging. The ArcGIS platform offers many options to share your findings with your coworkers, colleagues, and citizen scientists. So, by working with the Blue Planet team and leveraging these analysis tools, this project has really opened my eyes towards what's going on globally and that the larger problem is happening just in our backyard. Even though the results may look grim, there is an opportunity to make a change. Understanding precedes action. It is that action that will help save our planet. I'm reminded of the words of Sylvia Earle. She said, "I wish you could use all means at your disposal, films, expeditions, the web, new submarines, to create a campaign to ignite public support. While Dr. Earle's call to arms was focused on marine protected areas, the same Herculean effort are needed to address the wide range of challenges facing our oceans.